Greetings, peeps, for one of the final times of the year. It's been a while. Looking forward to this. Hydrostatics, fluids at equilibrium, which means simply not moving. So it's a fluid that is stationary and not moving. We start with a concept that we've covered earlier this year, particularly when we constructed snowshoes. We're a long way from snow at this point, looking towards summer. But we learned about pressure at that time, and we learned that force per unit area is the definition of pressure. And one of the things that made the snowshoes work was that we were able to spread out the force of one's weight over a larger area so you wouldn't sink in the snow quite as much. So pressure is force divided by area. This force is applied perpendicular to a surface. So over here you see in this box that represents the surface, and the force is pushing down in this case, and you can see this, it looks like an X, and that X represents into the board, because if you imagine an arrow, someone shooting an arrow, we would look at the back of the arrow, the feathers on the arrow, and we'd see the X, so that's in. The units for pressure are, well, force is newtons, area is meters squared, but we have named that unit after Blaise Pascal, a mathematician and scientist. So the unit for force is known as the Pascal, a Newton meter. Pressure also is a scalar value. Much like work is measured in joules, even though it has a force and a distance, it is actually a scalar, so it doesn't have direction. Pressure doesn't have direction, it just is applied to a surface, okay? Even though it's specifically in the direction that's perpendicular to the surface. Well, an object immersed into a fluid experiences pressure all over it, okay? The force is spread out over the entire surface of the area, all sides of that object. So what we have here is a cube, let's say, and of course I didn't draw the arrows on the other side of the cube, but we can imagine them to be there. We have a force that's pressing on this surface, creating pressure. We have a force pressing on this surface, creating pressure, and a force above creating pressure, and we would have one from below and the other sides as well, okay? So if you were swimming in water, if you just dived in the water, you're gonna have pressure everywhere pushing perpendicular to the infinitesimally small little perpendicular pieces of the surface area of your body. Actually, we feel pressure all the time. It's called atmospheric pressure. We exist in a fluid called air, which is 20% oxygen, approximately, mostly nitrogen, but this fluid enables us to, of course, breathe, but it has other features too. Air, although a gas, can behave like, it is considered a fluid, it behaves fluid-like, and so we'll see some properties of that in terms of what's known as buoyancy. So check it out. Pressure! Okay, and its relationship to depth. Like depth, you know, in a pool, deeper section, depth. That's what we're gonna do. We're gonna relate pressure to depth. Stay with me here. What we've got is a floating object. Things float in water sometimes if the densities are right. So we have an object and it's perfectly floating such that the top of this box is right at the level of the water. See? And so it's exposed to the air, and air has pressure associated with it. We call that atmospheric pressure. 1 atmosphere of pressure, all of the, basically, the air molecules above us that go all the way to the extremes of the atmosphere into orbit, is approximately on average 1.01 times 10 to the 5th pascals. So that's how we measure it in terms of pascals. All right, now this thing is being pushed down by that giant column of air, the atmospheric pressure, and it also has weight. So really it should be sinking, right? It should be falling unless something is supporting it. Well, what is supporting it? It is actually the water underneath. Somehow the water is able to provide a force, we call it the buoyant force, that is going to be pushing upwards to balance the situation out. Remember, this is static equilibrium, therefore this object isn't moving. So in the up-down situation here, we've got 2 forces down, force atmospheric, force of gravity. This is a perfectly floating object, so we have the buoyant force supporting the object in the fluid. We also have pressure on each side, but they're equal. If they wouldn't be equal, we would see acceleration in one direction or another. We've declared that this is static equilibrium. Therefore, the pressure on each of these sides has to be equal. And in a fluid like water, essentially that's what happens. Because object is in static equilibrium, what we notice here is that the sum of the forces in both the x direction and the y direction equals 0. There's no acceleration in the x direction, there's no acceleration in the y direction. So if we write our Newton's second law equation, it's been a while, but very important skill from this free body diagram. In the positive direction, we've got upwards F buoyant minus force atmospheric downwards minus force of gravity downwards equals 0, okay? 0 because there's no acceleration in the y direction. So over here, what we have is, we rearrange this, we can solve for force buoyant. The buoyant force is equal to the atmospheric force plus the force of gravity of that object. Okay, I'm going to write this in different terms, in terms of pressure, because what we want to do is relate pressure to fluid depth. So what I'm going to do here is notice that from before, the buoyant force is equal to pressure times area. So that's what happens over here. Pressure buoyant times the area that is underneath here. So this area that's underneath that box equals the atmospheric pressure times the area of the box, the same area, because it is a cube or a box or something like that, plus force of gravity, which we know to be mass times the acceleration due to gravity, mg. All right, well, what I'm going to do now is express mass in terms of the geometry of the object. Well, what does that mean? Well, this object has a particular size, and therefore it has a particular density. That mass has to fill this box to give it a certain weight. Okay, so there's a new character here that is called rho, R-O, R-H-O. So that's this character over here, and we call that, it's a Greek letter, R-H-O, rho. Okay, so we have one more Greek character. It's like a P with a little tail or something like that. It's mass density, which you guys have learned about probably in other science courses, perhaps chemistry, perhaps physical science. Mass per unit volume. In our case, that means m divided by volume. The units would be kilograms for mass, meters cubed for volume. Now we've done linear mass density recently for a string, but this is actual density of an object with its full volume, okay? 3 dimensions. Kilogram per meter cubed, okay? So if I do this, I notice that mass is going to be equal to rho times the volume. Rho times the volume, because it's density times volume will give me the mass. Now, volume of this cube can be expressed in terms of area, and you'll see why I do this. It would be the area here times the height, okay? The height of this cube. So I've substituted this in here, AH, for volume. Now I put it back in the original equation. So pressure buoyant times area equals pressure atmospheric times area plus rho times area, Hg. Notice that each term that I've underlined here in red has area associated with it. That's good, because if we have commonalities between each of the 3 terms, we can essentially divide by A and cancel all them out. So divide by A, divide by A, divide by A. No more area, and what we have here is this expression, that the buoyant pressure is equal to atmospheric pressure times rho GH. Generally it's written as rho GH. Just floats over the tongue much better than rho HG for me. Rho GH, rho GH, rho GH, okay? So density times gravity, acceleration due to gravity, times h. It is more commonly written as P2, some arbitrary pressure down below, equals an original pressure plus the added rho GH, which is h is the fluid depth. So that means that the deeper this box is, the more the pressure would be over here, because pressure, as we go downwards in a fluid, becomes greater and greater. So that the pressure is only dependent really on, well, yes, you have the initial atmospheric pressure here, but then it just depends on how deep you go. It doesn't matter if you go sideways, it's just up and down kind of situation. You've noticed, perhaps, if you have swam into the deep side of the pool, your ears, which are very pressure sensitive. We discussed this with the study of sound, that your ears are really great, your eardrum, at detecting changes in pressure. That's what sound is, it's a pressure wave. So in water, when we have pressure changing as a result of submerging deeper, we feel that. We definitely feel that. We have to pop our ears and stuff. Or if you fly on a plane where the pressure, you go higher and pressure is lower, even if you have a pressurized cabin, you're adjusting your ears all the time. Your ears are good they're very sensitive. They're good sensors for pressure. So yes, as we go deeper into the fluid, the pressure becomes greater and greater. And so that's kind of the idea, that we can use this relationship over here to use this idea that the deeper you go, the more pressure there is, and we can solve some cool problems, and we can relate it to something known as hydraulics. And that's it for today. So thank you. Morad out. Meh.